Now, after the discussion of gradient, divergence and curl, we have seen into the last lecture that how to interpret the physical meaning of gradient, divergence and curl. Now we have to convert. In the last lecture basically we have seen the meaning of gradient operator when this gradient operator operates on the temperature field, that is a scalar field. It gives a vector quantity. That quantity basically indicates the direction towards the maximum change, towards the higher point. And when I take the gradient of the potential, this is a field of potential and this is a positive charge basically. So in the surrounding of this I observe a field of the potential which is a scalar function. When I take the gradient of that scalar function, what I observe, that I observe a vector quantity. So that direction basically of that quantity is towards the maximum potential. Here darker portion is, the dark portion is indicate to the higher potential, higher temperature, and this higher potential. So this is the meaning of gradient, the physical picture of the gradient. Then after we had discussed about the divergence, if we take divergence of any vector field, then what we get basically as a result. So when a divergence of any vector field is a scalar, that means a magnitude only, and magnitude could be 0, positive or negative. So further, what is the meaning of when we get the result positive, 0 or negative? So in the last lecture we had discussed about this, कि positive or the result is positive of divergence of any vector field, that means is spreading, the field is spreading. The source, there is the source, from that basically line is coming out. And when the divergence is negative, that means flux, electric field lines or magnetic field line are converging. For when 0, it means the electric flux basically enter through this open surface and the amount is same. When the electric flux or magnetic flux comes out from the other faces, so this time the total electric flux basically is 0. So this was the physical interpretations, physical picture of the divergence. And into the third one we have seen the geometrical picture of the curl. So in case of we have considered here that this is the magnetic field which is rotating basically into this plane. This is x axis and this one is the y axis plane. In xy plane our curl is into the xy plane, so field is rotating basically. So we have to find out the rate of the rotation and magnitude, direction as well as. So we can find out this with the help of curl. So in Ampere's law we have seen that if suppose current carrying conductor is along the z direction, the magnetic field basically develops around that. That magnetic field is representing by this circle and the direction with the help of these arrows. So I have to find out the rate of this curl. For that I have used this formula del cross B. I can find out the direction and magnitude at this point P1, point P2, point P3 and so on. The curl basically is into the xy plane and the direction of this axis basically of this rotation will be along the z direction. The result of this curl will be along the z direction. So this is the physical picture of the curl. And after understanding the idea, the physical concept of the gradient, divergence and curl, Now what we have to do, we have to basically study the basic four laws in electricity and magnetism. Gauss law in electrostatics, Gauss law in magnetism, Faraday law, and Ampere's law. These are basically four important laws into the electrodynamics, and we have to convert the integral form of these four basic laws into the differential form. But before that, we have used some mathematical statement of the Gauss divergence theorem and Stokes theorem. So these are the fundamental theorem of the divergence, this Gauss divergence theorem. So our purpose is for this course basically we have to use only this mathematical statement that explain about the closed surface integral of E dot ds. Basically this is the flux, electric flux that is coming out from the closed surface, as we have seen into the Gauss law. So this electric flux which is coming out from the closed surface is equal to the divergence of the electric field within the volume that is enclosed by the closed surface. If I consider a sphere here, this is a sphere, a positive charge Q is kept at the center of this sphere. So electric field lines which are coming out from the surface, that will be total electric flux, and this total electric flux we can measure with the help of this mathematical formula E dot ds. We have seen this into Gauss formula also. So for that what we have to do, we just consider a small elementary area ds, and we assume that electric field line also passing through this, that is constant everywhere at the surface. So that is E dot ds is the electric flux which comes out through this small elementary area ds. So that will be d phi. So suppose I want to find out the total electric flux through that closed surface, then I have to take the closed surface integral of this quantity E dot ds. So E dot ds, closed surface integral of E dot ds, is the total electric flux. These electric field lines basically is the total electric flux, or with the help of the divergence of the electric field we can also measure the electric flux. So these are the basically two terms, through the closed surface or within the volume. That volume basically, now if suppose I take the divergence at these points, here, at every point I take the divergence. So basically what I am doing, I am just measuring the electric field lines through that. So sum of these divergence within this volume will be automatically, that will be electric flux. So Gauss divergence theorem states about the electric flux within the volume or flux which is coming out from that surface, closed surface. So it means that surface integral of any vector field over a surface, over a closed surface, is equal to the volume integral of the divergence of the same vector field over the volume enclosed within that closed surface. So the volume enclosed by this closed surface, in which if we will measure the divergence of that electric field, that will be equal to the electric flux through this closed surface. So you can measure the electric flux by this way, or you can measure the electric flux within the volume by this way. So ultimately we are getting the total electric flux. So this is also a relationship between the surface integral to the volume integral. If you want to convert this closed surface integral into the volume integral, you can use this formula. So this is the Gauss divergence theorem. which we will use to convert the integral equation into the differential form. Next is the fundamental theorem of the curl, that is known as the Stokes theorem. Here closed path integral E dot dl. This is closed path. Suppose this is in tangent E and this is the center of the square. dl is a small segment. Vector dl is a small segment on this circumference of the square. So direction of this will be towards the length of the wire, and this is E. E dot dl means this complete cycle, the total circumference. It indicates to the potential bus, but here what we are showing the closed path integral E dot dl. This total E dot dl will be equal to this is the open surface. If we consider a small segment of the curl, we take the curl of a small portion within this open surface and add to all of them, then we will get the bigger one circle, this this last one. Addition of these small curls within this open surface will be equal to the large one. So curl. So this equation, Stokes theorem, basically states that the line integral of any vector field, here vector field we are considering electric field, around any closed loop, this is our closed loop, is equal to the surface integral of the curl. Surface integral of the curl, this is open surface, integral of the curl of the same field E we are considering here over the total surface enclosed by that closed loop. This closed loop encloses this open surface, and into this surface we are considering a small portion of the curl, and some of these curl basically indicate to this large one. So both are there are two different ways to explain this. So this E dot dl is equal to, in terms of the open surface integral, del cross E dot ds. Because del cross E is a vector, that will be a vector quantity, and this ds area vector ds. This result of this del cross V will be a vector quantity. So closed path integral E dot dl is equal to open surface integral